NanoHub U, online instruction.
Hey everyone, welcome to lecture 412. So we're continuing on the topic of using a vectorized BPM method to solve the modes of a photonic crystal fiber. And so if you recall, photonic crystal fiber has the unique property that it can create mode confinement within either low index or otherwise unguidable region based on traditional index wave guiding. And then here's a depiction of the modes that would be created in a photonic crystal fiber. And so you can see here that there's essentially this lowest order mode, which is kind of a circular shape. And then there's one with kind of this frilly pattern, which basically reflects a different azimuthal quantum number. And so in this case, this would be called m equals 3 mode. And then sometimes this would be called m equals 0 mode. And so this is just two examples of some of the fundamental transverse electric modes that are available as depicted by the HY component. So that's in the plane. And then this is actually an example of the overall confinement loss as a function of wavelength for different parameter values. And remember that d over capital lambda, it tells you the ratio of the diameter of the air holes that are extended into cylinders in the photonic crystal fiber compared to the periodicity or spacing between them. And so you can see that as the amount of air holes actually increases in volume by basically a larger d over lambda value, then the confinement loss actually decreases quite substantially. Remember that this y-axis for confinement loss is a log scale, and then all of the losses decrease as you go to higher wavelengths, lambda, and so that actually is not surprising at all. So the overall effect is obviously dependent on multiple parameters at the same time. And so depending on the application you're interested in, you could consider using large d over lambda and large lambda to have very good mode confinement, or if you need coupling, it could be increased. And then this is actually showing how the effective mode area depends on the period. And so it's actually interesting about this is that for both values of d over lambda, you actually have a nonlinear behavior, and actually the greatest mode confinement is happening around 1 micron period, and then it increases in both directions. In the first case, when you go to larger periods, it increases basically because each of the periods is more spread out, so that kind of makes sense. But in the other case, it's actually increasing because of a different mechanism, which is just that you don't have as good photonic crystal behavior at that point. And then this is showing how the effective index actually increases modestly as you increase the period. So this is consistent with our previous result on the loss, but it's just showing that if you have an increase in the effective mode index, then there's more confinement in the other directions. And then finally, you can see that the dispersion relation, the effective index, is actually increasing quite consistently as a function of the wavelength lambda. And then if you look at the dispersion, which is derived from the previous graph as the second derivative of k with respect to omega, then you can actually see that depending on the exact value of d over lambda, you can have potentially purely rigor dispersion, or you can have anomalous dispersion, or you can have multiple crossover points like here for this d over lambda equals 0.7. And so this would really depend on your application. Of course, typically for most long distance communication, you'd want mode dispersion to be close to 0. On the other hand, in some cases, you may want mode compensation or dispersion compensation. And so whatever mode fiber it was connected to, which has one sign of dispersion, you may need the opposite sign for some length to kind of cancel out the net dispersion. And of course, this is dispersion primarily induced by the presence of the structure and there could be additional dispersion from the choice of materials, which I don't think is included explicitly in the simulation. In the next presentation, we'll explore more about other types of photonic crystal mode confinement systems.